Can you see the screen?
Yes,
Yes.
sir.
Okay. Yes. So these are output side. So we indicate and the output side the voltage. What happened? Go back. So indicate a voltage here V naught. This output voltage. So this is what we call our basic current mirror circuit. The voltage here is VBE. current that flows here, this is our collector current IC. And let's call it IC1 or Q1. And this one IC2. So now today we'll see the effect of the final value of R naught, how this output raised to R naught affect the gain and the error of the current mirror, right? So while we investigate this effect of R naught, we ignore the effect of beta, right? We consider one factor at a time. We already discussed the effect of beta, and we didn't consider, now we just see the effect of R naught, we ignore the effect of beta. Ignoring the effect of beta means assuming beta to be infinite, right? Not finite. If you assume beta infinite, that means your IB, which is IC by beta, will be 0, right? So basically there will be no base current flowing. So ignoring the effect of beta, that means same as assuming the base currents to be 0, right? So that is what it means, right? Ignoring the effect of beta or assuming beta to be very high so that these currents are negligibly small, and IN is almost IC1, right? So this shows that IN will be IC1. Right? So now we need to consider the effect of the output resistance R naught. So if you want to consider the effect of R naught, how it affects the performance of the current mirror, so we show them explicitly, though they are built inside the transistor. But now, in order to take the entire effect into account, we show them explicitly. So R naught is a resistance that is between base and collector. So that's, we can show like this. Sorry, emitter and collector. Since the emitter is ground, so this also goes to ground. So let's call it R01 for Q1. And similarly, we'll have a resistance here for Q2 between collector and emitter, and we call it R02. So these are the two output resistances that will be connected in parallel, right, to the transistors. And now you see that so there is a parallel path, and IC is flowing in this direction, and there's another parallel path, right, to this path of the IC, the collector currents. And since there is a voltage here, right, so this is the collector voltage, the collector side. So the voltage, you can call it VC, collector voltage VC1, right? And there will be a current flowing here, right? And that will be the voltage divided by the resistance, right? R01. So in addition to this collector current IC1, the another current will flow, right? That is the voltage divided by this output resistance through this parallel path. Right? Similarly, through R02, we'll have the similar current, which is V naught divided by R02. Right? Is that clear?
Yes, sir.
So I input current now when we consider the effect of finite beta I in will be equal to IC1 plus the current that is flowing here to IB. Now we are ignoring that part. Now considering the effect of finite R naught, so now we get this current, right? This additional current that will be added to IC1. So I in now that I wrote here, the IC1, not just IC1. So to this we have to add VC1 divided by R01. So that will be our input current. And similarly, from the output side, you see that we can write, okay, let's change this one. The output current we can write I out is IC2 plus V naught divided by R02. Okay. Now what is R naught, right? What is the expression for this output voltage R naught? Do you know? What is the expression for R naught?
VA by IC.
Right. So R naught is written as VA. VA is called the early voltage divided by IC. So that's the expression for R naught. So R naught is also a function of the collector current IC. So the output current we can write as IC2 plus we have V naught, and the denominator we have VA, and that divided by IC, in this case IC2. Now VA is a constant for a particular transistors, and for different transistors can have different values of VA, like beta value. But here we are assuming that these two transistors, they have the same, they're identical. Everything is same for these two transistors. And that means that they are the same emitter cross-sectional areas, AE same, right? And they have the same base to emitter voltages. So that means the two collector currents will be same. IC1 will be equal to IC2, right? The two collector currents are same. And that we can say is, let's just put them as IC, right? So, so if we substitute for IC for IC1 and IC2, then now this expression here we can express as IC, replacing IC2 by IC1 plus V naught by VA. Now this is how we can express the I out. Similarly for I in, we have IC1 and plus VC1, then divided by VA. Now R naught 1, since the collector current is IC1, so VA by IC1. And IC1 we replace by IC, and then we can write as 1 plus, this is VC1 by VA. So now we have got the expressions for the output and the input current. So now you can write the expression for the gain. Gain is I out by I in and that you have IC 1 plus V naught by VA. And IN you have IC 1 plus VC1 by VA. Right? So after simplifying this, we can express this as 1 plus V naught by VA, that divided by 1 plus VC1 by VA. So that's the gain expression. And what will be the error? Error is our actual gain, which is I out by I in, and minus the ideal gain, which is 1. So now substituting this, that minus 1. So after doing the math here, so this we can express as, so in the denominator we have 1 plus VC1 by VA, and you have here 1 plus V naught by VA minus 1 plus VC1 by VA, right? So here 1 and 1 will cancel out, and we will be left with V naught minus VC1 divided by VA, then by 1 plus VC1 by VA. Now, what is VC1? Okay, V naught is the voltage at the second collector, right? So V naught is same as VC2. Right? V naught is same as VC2, so this also we can write as VC2 minus VC1, that divided by VA, and that divided by 1 plus VC1 by VA. Now I have written in this form because it's that make it easy to remember. And VC2 minus VC1, the difference between these two collector voltages. So you can write as del VC, right? Del VC by VA. And that divided by, now what is VC1?
So TCC minus I in R.
That's too complicated, no?
Okay.
VC1 is VC1 is VBE, see, it's the same point, right? The base voltage here.
Yes, sir.
VC1 is VBE, so you can write 1 plus VBE by VA. Now VA is large, usually 50 to 100 volt, whereas VBE is less than 1 volt, right? So what we get here, that VBE by VA will be much smaller than 1, right? Most cases. If that is, but you can ignore this part, VB by VA, and if you ignore that, so what you end up with? You end up with del VC del VC by VA. So that is how we can express the error, right? Which is also we write in these forms, the Greek letter E. So error we can express, right, as a del VC by VA. The difference between the two collector voltage divided by the early voltage. Is that clear?
Yes, sir.
So let's take a numerical example. Let's say that so you see that the error here depends on the output voltage, right? How much is V naught and the early voltage of the transistor. The higher is the output voltage, the higher will be the error because more current will flow, right? Whereas this here is only VBE, right? So current flowing here is less. And also the value of R naught, right? If R naught is low, then error will be large, right? So let's say our output voltage V naught is 10 volt and VA, let's say, is 100 volt, right? So how much will be the error then? Hmm?
Sir, 9.3%.
Right. So in this case, del VC, which is VC2 minus VC1, VC2 is V0, VC1 is VBE, VBE is 0.7, so you get 9.3 volt. So here you get 9.3 divided by VA is 100, so 0.093, or in percent, 9.3%. So which is quite large, right? So now how do we minimize this error, right? What are the ways to minimize this error?
So we need to increase the output resistance.
Right. If you can increase the output resistance, then this current will reduce, right? And error will reduce, right? So in order to reduce the error, we need to increase the output resistance. And what are the ways we can increase the output resistance?
Sir, adding a common collector.
Common collector, how common collector?
The common collector has highest
Low
input
output resistance. Common collector has low output resistance. You know? We're talking about the output resistance.
Okay.
So there are two ways to increase the output resistance. One is to insert a resistance in the emitter circuit. If we have a resistance in the emitter, that will increase the output resistance. The other is the cascade configuration. The cascade configuration has a very high output resistance, if you remember that. So there are two ways, right? To increase the output resistance. One is the insert emitter resistance. Other is to use cascode configuration. Right? So first we use this insert this emitter resistance. We are using emitter resistance to increase the output resistance. So the V1. So now when you insert this output resistance, so insert the emitter resistance. So what is the output resistance?
Sir, R naught into 1 plus GM R pi parallel R.
So R naught is to 1 plus GM2 that times
R pi.
RE in parallel with R pi. Right. So before the output resistance is only this small R naught. Now this is being multiplied by this factor. So that is much larger now. And that is small, the R naught 2 is VA. divided by IC2, and that times 1 plus GM2 RE in parallel with R pi 2. And that is written as VA prime divided by IC2. The resistance is voltage by current, so this is now effective our early voltage, and VA prime is VA times GM2 RE in parallel with R pi 2. So that is our effective. And what will be the error now?
It will be much lower, sir.
How much will be?
So by this factor 1 plus GM value.
It will be del VC divided by VA prime. Okay. So the same expression, just VA, the early voltage is now is changed. It is VA prime, the new early voltage, and that is given by this expression. Is that clear?
Yes, sir.
Now, apart from improving the error due to the output resistance, this RE can be also used for some other purpose. And what is this some other purpose?
So controlling the gain.
Controlling the gain. Let's see. Say you are using two different values of RE here, RE1 and RE2. Okay. Different resistances. So if you use different resistance, then the current will be also different. Let's say this is IE1 and this is IE2. Since the voltage has to be same, these two are the parallel branches. The voltage here is the same node, right? And the voltage is VB, right? The base voltage to the ground, right? So these voltages we can express as on the left side, this is VBE1 plus I1 RE1. And on the right side, we have VBE2 plus I2 RE2. Now, if we assume that these two forward bias voltages, VB1 is same as VB2, okay, which is VB, the forward bias voltage, then this we can simplify to I1 RE1, and that's equal to I2 RE2. And we have E, right? IE1 and IE2. Then this, from this we can write that IE2 is equal to RE1, RE2, and IE1. Right? So you see that if you want that IE2 to be 2 times of IE1, double the IE1, then you choose this ratio RE1, RE2 equal to, right? That means the resistance RE2 should be half the resistance of RE1, right? RE2 should be half of RE1. Then the current will be double. And since this is the emitter current, this is the collector current, so this is almost same, right? And I out will be alpha IE, and this one will be almost equal to IE, right? So by choosing the appropriate ratio for these two resistances, we can accordingly increase or decrease the current, right? If you want this current to be 10 times of this current, then this resistance you choose 1/10 of this resistance, right? So that is how we can adjust the current, right, in the output side, right? So apart from improving the error due to the finite output resistance, this can also help us to adjust the current, right? Change the value of the current. Any question?
No, sir.
Yeah, this is very useful in discrete circuit. If you are designing a current mirror circuit using discrete circuit, right? So you can easily adjust the current by this emitter resistance, right? Because in discrete circuit, it's difficult to have the change the area, right? The transistors are already built, right? They are finished product, and you cannot change the size of the transistor. But by incorporating the resistance and adjusting their ratio, you can adjust the current, right? The output current. So this is very useful for when you are using in discrete circuits, this current mirror. Okay. So that is how we can improve the input rate, sorry, we can improve the performance, reduce the error due to the finite output resistance by inserting the emitter resistance. And next we will see in the cascode configuration. Okay, go to the next one. Okay, before that, I would like to show one more thing here. So we address this issue of this output resistance in the current mirror circuit. Now, and before that, we discussed about the finite beta and how to reduce that error. And then we can combine these two, right, technique for finite beta and finite output resistance in one circuit. So in one circuit, by inserting these resistances, emitters in the emitter, you improve the resistance, you improve the the error due to finite output resistance, and by inserting this Q3 beta helper, we improve the error due to the finite beta. Right? Okay, so now next we come to the second method, the cascade current method. So this is known as the cascade current mirror. You remember the cascade amplifier, we had the common emitter, then we had the common base, right? So this is similar, right? So two current mirrors on top of the another, or cascade current mirror. So voltage here is VBE. That is the base to emitter voltage. And since these two are our basic current mirror with their bases tied together, and the current IC1 here will be same as current IC2. Now the error will be determined by the resistance of the circuit, the output resistance here. Right? And what will be this output resistance? Any idea?
Sir, same as the previous one, but there will be another R naught instead of RE.
Yeah, you're right. So basically here, what like this, the emitter side, and what is connected here at the emitter, basically the output resistance of this transistor is called R02. And that's the output resistance that is connected to the emitter, and there is nothing but a small R02, right? So basically the circuit, if you look from the output of the Q4, basically it simplifies to this circuit. Here we have R02, and that is our Q4. And okay. and we're looking from here, R naught, right? We have E naught here. So the circuit will look like this. You can also call it equivalent circuit from the output side of Q4. And here the R0 will be the small R naught, let's call it the 4, and that times 1 plus GM4, and that times small R02 in parallel with R5 4. Right? Now, in general, the R naught will be much larger than R5. So this we simplify to R0, 4, and then 1 plus GM4, and this R5 4. Yeah, this is much greater than this. Now, what is this product GM R5?
Sir, RE.
No.
GM R5. So GM is equal to IC by VC, and R5 is equal to
Okay, we'll wait for the Adhan to finish and then continue. So what is JMR5?
so beta.
Right, JMR5 is beta. So we get the R04 1 plus call it beta 4. So dropping the subscripts, we can just write R naught times 1 plus beta. Right? So this shows that the cascode configuration has very high output resistance, because R naught, which is already high, that getting multiplied by 1 plus beta will give you a very high output resistance. And then this we can, R naught is VA by IC, times 1 plus beta, and that we can write as VA prime, or effective early voltage, where VA prime is VA times 1 plus beta. So there is a significant increase in the output resistance, and the error will be del VC divided by your VA prime, right? And VA prime is this. So the cascode configuration will give you a big improvement in terms of the error due to the finite output resistance or not. And what is del VC in this case?
So V naught minus 2 VB.
So del VC, right? First we can write VC4 minus VC3. Right? VC4 is the voltage here, the collector of this VC4, and this is our VC3. Right? So del VC, and what is VC3? You say we have VBE here, and then we have another VBE, base to emitter voltage. So VC3 is actually 2 VBE. So this is V naught minus 2 VBE. So that will be our del VC. And that is how we can determine the error. What will be the current, the input current expression for the I in? Hello, you are going to sleep.
Answer.
It's very easy, no? It's Ohm's law.
Good answer.
What?
VCC minus VC3 into R.
VCC minus VC3
Into R.
into R?
Sorry, sir. Divided by R.
Good. So VCC minus VC3 we have already determined 2 VBE, and that good bar. Now, what's the error due to finite beta? Right? That is the error we have determined for output resistance R naught. Now, what is the due to finite beta? Right? No, that is not that straightforward. When there's number of steps you need to do. Start again. So if you want to determine the error due to finite beta, you have to do some analysis here. The current, you have to find the currents. Let's say this is IB3, this is IB4, right? And then this is here, you have 2 IB, right? One going here, the other going here. So the current here is IB3 plus IB4. And then you can write that I in is, this is your current here, IC3, IC3 plus IB3 plus IB4, right? And then here you have IE3, and IE3 will be IC1 plus 2IB, right? And since the bases are, we have assumed the tied together, they have the same base diameter voltages. So IC1 will be IC2. Now here you see that voltage here is VBE, and voltage at this point is 2 VBE, right? And then you have another drop here, and you get also voltage VBE, right? So at both these collectors, voltage is VBE, same voltage. Del VC is 0 here, right? So you don't have that error, right? The difference in current due to output because the voltage is same. So IC1 will be IC2, right? And then you have expression for I out, right? Which will be this. You have this here, IE4, which will be I out plus IB4. Right? So by solving all these, right, equations and assuming that beta is much larger than 1, if you solve all these equations and assume beta is much larger than 1, then error which is expressed as I out by I in minus 1, that will be approximately 4 by beta, which is twice the error that we got, right, for the basic current error. So while there's a significant improvement in the error due to finite output resistance, the error due to finite beta, it gets worse, right? It increases. And that is only logical because you see this current I input current now has to supply the base current for these 4 transistors. So all the transistors, the base current basically coming from this I in. Right? So the error is now 4 by beta. Error is worse. So that is the downside drawback, right, for this cascade current mirror. The error due to finite beta gets worse, right? Any question? No question. Okay, so now we show another interesting circuit that is known as called the Wilson current mirror. So this circuit is known as the Wilson current mirror, and this one uses 3 transistors. So you see that this little bit twist here. The in the previous all cases, the Q1, the base to the collector was tied, right, shorted. Now in this case, the base to collector of Q2 is shorted, right? So that is the change, and here you have only 3 transistors. So in this case, this is your VBE, base to emitter voltage, right? So voltage here is also VBE. And then you have another VBE here, right? So voltage at this end, this is 2 VBE, right? So in this case, your input current is VCC minus 2 VBE divided by R. So that is the same as what we got for the cascode current mirrors, similar expression. Now, what is the output resistance here? Right? That will determine how much improvement we get. Right? Now, still, this is a cascode configuration from the output side, because this is like common emitter, common base. Right? So to find R naught, then we need to see what is the resistance from here. Right? Let's call it R02. Right? How much is R02? Now R02, you see that this is connected to Q2. So obviously we have this, what we can call it a small R naught, right? Between collector and emitter. And then this is another branching out connected to the base, right? So then you need to see what is the resistance coming from here, right? How much is the resistance from this side? Now this side is connected to the 2 bases, right? And so that is the resistance that will contribute to this total resistance. So resistance coming from each of the input, right, of these bases. So here the resistance is R pi, and here also R pi, right? So these two R pi, they have a common node. So they are in basically parallel configuration. So parallel, their combination will give you R pi by 2. Right? So is that clear?
Yes, sir.
So what will be your R02 then?
Sir, R naught to parallel R by 2. R pi by 2.
Right. So now if I draw the equivalent circuit from the output side, so it will look like this. This is our Q3 transistor. So output side, and looking from here, R naught. And this is our resistance R02. And this will be parallel combination of R02 and R pi. Okay. So now what we can write for R naught? Now since R naught, we can, sorry, R pi by 2. Now since R naught, the output resistance is much larger than R pi, so we can easily simplify or approximate this to R pi by 2. So now this the output resistance looking from the collector of Q3, that will be small r03, and that times 1 plus gm3, and that times we have here r pi by 2, and that will be in parallel with r pi of Q3. Is that clear, guys?
Yes, sir.
Now, if we assume that these all our parameters are same, r pi same as r pi 3, for the sake of our simplification of analysis, and we drop the subscripts, so we write just r naught, and that will be 1 plus gm, and this parallel combination will be r pi by 3. And now this further we can simplify to 1 plus, and gm r pi is
So beta.
gm r pi is beta, so it will be beta by 3. And now this we can write r naught as va by ic, 1 plus beta by 3, and this is we can write as va prime by ic. Va prime is our new early voltage, which is va times 1 plus beta by 3. Now this new early voltage, we have Va getting multiplied by 1 plus beta by 3. It's not as large as what we got for the cascode current mirror. In the cascode current mirror, it was multiplied by 1 plus beta, and it is now almost 1/3 of that, but it's still, I mean, quite large, right? It's quite large because beta is large, so it's still quite large, and that will significantly reduce the error due to finite output resistance or not. But what is the beauty of this circuit is the improvement in the error due to the finite beta, right? In the previous cascode current mirror, the error was double the error of the basic current mirror circuit. And now in this case, you see that since now this is changed, this connection is changed from Q1 to Q2. Now I in is not supplying all the base currents, right? Because of this little twist in the circuit, now you see that I in is only supplying the base current of Q3, IB3, right? This part goes to IC1, right? And other part goes to IB3. So it is supplying the base current for only basically Q3. The other base currents, right? The IB and IB here, right? Will be coming from here to IB, right? There is part of this coming from I out, right? So I out has to share, right, some of the burden of this extra base current, right? And part is shared by I in. So because of the sharing of these base currents by the two sides of the currents, now the error due to finite beta, what we get is minus 2 by beta square. And of course, there's many steps of analysis before you get the, like we showed for the cascode current mirror. So similar by equating this different, writing the equations for different currents. It's basically application of KCL, no? And assuming that beta is much larger than 1, then we can get this error, which is minus 2 by beta square, that what we got right, using the beta helper, right? So significant improvement also in the error due to the current gain, the finite current gain. Right? So, but just by using 3 transistors and Wilson current mirror, it succeeded in improving the error due to both the finite output resistance and not significant improvement in both the errors uh, and the error due to the finite current gain beta. Any question, guys? So this is a very ingenious solution, right, to the problems and the clever design. Guys, any question?
No, sir.
It all understood?
Yes, sir. Sir, can you just go to the previous slide?
Okay.
Uh, Sir, how we got 4 by beta there? What is I not? I out.
What is I out? This I out.
Yes, sir.
This I in. So
Yes, sir.
you have to write all these equations now. You have to write all the equations for the different transistors and then solve them, right? And finally get the expression for I out by I in, subtract 1, and then assume that beta is much larger than 1, then you can get this. And this is only logical. This makes sense because I in is supplying the base current for the 4 transistors, right? All these base currents, these two coming from this side, right? So that is coming from I in, and also these two also coming from I in. So it is supplying the base current for the 4 transistors, and so you get 4 by beta. And that's only logical. We have shown in the previous the basic current mirror. The error is equal to n by beta. N is the number of transistors, right?
Okay. Yes, sir.
And this is the, we can also extend this for multi-stage amplifiers. If you want to extend this for multi-stage amplifiers, you just connect more transistors here, right? Something like this. Then it goes, right? And so that will be Q4, Q5, right? This is I out 1, and you get I out 2.
Sir, there is no current controlling option other than the cross-sectional area, right?
Yeah, yeah.
Okay.
So basically, we introduced to the current mirrors, current sources, current mirror circuits, how to construct the different current sources and current mirror circuits, how to improve the performance, how to reduce the error, right, by introducing the emitter resistance by and or cascade configuration, and then finally Wilson current mirror, how to steer the current for multi-stage amplifiers. Right? And with that, we conclude our discussion on the current sources and current mirror circuits. And next, we'll discuss about the active load. It's another important component of the integrated circuits. Any question, guys?
Sir, is this our last week, or we will have classes in the next week as well?
No, no, no. We have one more week now, so we'll discuss the active learning our next week and the
So
two
next week
classes.
we have two
Mm.
classes.
Right, right.
Okay.
So, what will be our final exam date?
Sir, 5th or 9th of January.
Fifth. Ninth is too late, no? Fifth will be fine, right? So, fifth. Fifth is Tuesday, no? So,
Uh,
Sir,
we have
sir,
another final on that day.
Tuesday we have another final, sir.
what final?
Sir,
The
control.
control.
Uh, control, what time do you have?
This
Sir,
is not fixed yet.
yes, sir.
Uh,
Sir, can you take the exam on the usage time, sir? It was given 7 January.
really?
Yes, sir.
7th
Sir,
January,
Y-
Thursday.
Yes, sir, 7th January will be fine.
so many
What?
of us has finals in 7th.
What?
Sir, many of us is on 7th. We have already one final.
What final? So, 7th is our usage date, no? So,
CC
that,
330.
that is our, we are entitled to take it on 7th.
Yes, sir.
Sir, can you take it on 9?
No, no, that's too late.
So 9th
Because
will be better for us.
Yes, sir.
by 11th, we have to submit all the grades. So,
Then sir, 8th.
November.
Sir, as there are many students in the section, some of them will have exam different dates on different. It will be better if you take on usage date, because if someone other have the exam, they may ask that faculty to not take the exam on that 7th, because the UC is already set with 7 with opto take with analog.
Yeah, that's why we say, because we are not finding any suitable date because all dates are booked by one or the other exam, and we are entitled to take the when that is given by the central authority, you know. So
Yes, sir.
you should not argue with that.
Yes, sir.
So let's fix it on 7th, and what will be the appropriate time for the exam?
Sir, 6 p.m. or 7 p.m.
Sir, in
6
the
p.m.
evening.
Yes, sir,
evening.
6:30.
Okay. So tentatively, it's we fix the time around. I mean, after Maghrib, 6 or 7. And if there is some clash, then we might change it in the morning, right? If you, I mean, if some of the students they have exam around the same time, we can bring it up in the morning. Otherwise, we fix it on 7 at around 6 or 7 p.m. Okay,
Okay, sir.
right?
স্যার
Okay.
স্যার
Yep.
স্যার আমাদের মিড মার্কসটা কি বলা যাবে বা কোনোভাবে?
I have not done with checking the scripts yet, so let's see if I can show it in the next week.
ওকে স্যার, অ্যান্ড হচ্ছে স্যার আমাদের নোটস হ্যান্ড নোটস গুলো কি থাকবে আর কি পোস্ট করা হবে যে লেকচার 12 থেকে?
হ্যান্ড নোটস কিছুটা আছে, কিন্তু সমস্যা হলো আমাদের যে টিএ ছিল, she was preparing the hand notes. She is sick now. She has become sick.
ওকে স্যার।
So up to a couple of lectures I can provide you the hand notes, but rest I'm not sure. She is very sick.
ওকে স্যার, তাহলে যে যতটুকু দেওয়া যায় ওটা দিলে হয়তো আমাদের হেল্প হবে স্যার।
Okay, we'll do that. No problem.
ওকে স্যার।
সিলেবাসটা কি
Syllabus for what?
ফর ফাইনাল? Will it be after
Whatever
mid?
discussed in the class up to next week's lecture, we'll cover we have finished the conveyor circuits, and next week we'll cover the active load, and that will be the syllabus. Probably, yeah, yeah, up to active load.
মিড সিলেবাস কি ইনক্লুডেড থাকবে?
That's up to you. If you want it to be included, we can include it. If you want it to be excluded, we can exclude it. Which one you prefer?
স্যার ভালো হয় হয়তো।
স্যার এক্সক্লুডেডই ভালো হবে, কারণ অনেকগুলো লেকচার মিডের পরে।
Sir, we could focus after mid more precisely. From mid to
What?
final, sir, from mid to final we can focus more if the mid
Oh,
syllabus
oh,
excluded. It will be better for us. We
okay.
can focus
You can
more.
focus better. Okay. Okay. So we'll limit the syllabus from after mid to whatever we can cover in the next lecture next week.
Thank you, sir.
Okay, guys?
Inshallah. Thank you, sir.
Okay, no problem.
Sir.
Yes.
Oh, one more. In the assignment, should we use one ID for each member?
Assignment
স্যার প্রজেক্ট।
Project. Sorry, sir. Project.
project. What is the question?
স্যার আইডি নাম্বার দিয়ে করতে হবে তো স্যার, তো আমরা তিনজনের মধ্যে যে
Yeah,
কোনো
this is a group project, no? So
Yes, sir.
use one of your
Anyone.
ID, one of your student, yeah, anyone's ID.
Okay, sir. Okay, sir.
Yeah.
থ্যাংক ইউ স্যার, আসসালামু আলাইকুম।
Walaikum assalam. Okay, guys, see you next week. Allah Hafiz.
Assalamu alaikum.
Yes, sir. Take care, sir. Assalamu alaikum.
টেক কেয়ার।
Fahim?